Hello everyone, this is my second lecture on acid-base chemistry. Earlier we have discussed the Arrhenius concept, the Franklin solvent concept and the Bronsted-Lowry concept. So the Arrhenius concept was the primitive concept which were involving only proton and hydroxyl ions. Then the theory was gradually extended, and in the Bronsted-Lowry theory we had the theory of acceptance of proton or donation of proton. But all these theories had certain limitations, such as they need a solvent, or they need to involve some proton or hydroxyl ions. But in case of such as oxides or the substances which do not dissolve in any solvent, in those cases how would their acidity and basicity should be standardized. So our next topic is our fourth concept on acidity and basicity, which is the Lux-Flood Concept, which is mainly for the oxides of different substances. So the acid-base behavior is described in terms of oxide ions here. This concept was advanced to treat non-protonic systems. So the systems which do not involve any proton and which were not amenable to the Bronsted-Lowry definition. The usefulness of this theory is mostly limited to the molten oxides. Here an oxide which is acidic in nature, when reacts with a base which is another oxide, then the salt formed is known as the adduct. Here the acid is called the oxide acceptor, while the base is called the oxide donor. So according to donation or receiving of oxides, they have been defined as the acids or the bases. So the highlighted feature of this theory is the non-protonic reactions involved and at high temperatures for inorganic salts, inorganic melts. So we have calcium oxide, which is a base, silicon oxide, this is silicon oxide, which is an acid. When they form a salt together, calcium silicate, this salt is known as the adduct. Now their strength, acidity and basicity strength, can be measured on thermodynamic data. This is known as the acidity parameter. So this is completely an experimental data. So acidity parameter is A, small letter a. For acid it is A suffix capital A, and for bases it is A suffix capital B. But in general we write the formula of the substances which are involved, such as if it is calcium oxides, then it is A suffix calcium oxide. If it is silicon oxide, then it is A suffix silicon oxide, like this one, A suffix calcium oxide, A suffix silicon oxide. And these are all obtained from the thermodynamic data, and this data is the enthalpy of the reaction. Suppose we have this reaction, calcium oxide and silicon dioxide. So the thermodynamic data from this formula, AB minus AA whole square equal to delta H, and if delta is negative, then this value is also negative. If delta H is positive, then this value is also positive. So from that consideration, this value has been found to be minus 8.4. Now if calcium oxide is 0, then this is plus 8.4, or silicon oxide is 0, then calcium oxide is minus 8.4. So we need to have some standard data. We need to have some data which would calibrate them. So here water, the universal solvent, has been exclusively used, and its parameter has been arbitrarily taken to be 0. Okay, so if silicon dioxide reacts with water excuse me, then we have found that the AB minus AA value is minus 0.9. So since water has been arbitrarily taken as 0, then the value for silicon dioxide has been minus 0.9. If this minus 0.9 value is put here, then it is found that the value for calcium oxide should be minus 7.5. Okay, so this is the acidity and basicity parameter which can be obtained from the thermodynamic data according to the Lux-Flood concept. Now we have a problem here that ferric carbonate is an unstable compound. Okay, why ferric carbonate is an unstable compound? Here we find that ferric oxide Fe2O3, during its formation, if it is an adduct, then it is from the combination of ferric ion and oxide ion, and this is a very ferric ion is very strong oxide acceptor according to Lux-Flood concept, and it is reluctant to coexist with carbonate ions. This is explained on the following basis. When ferric oxide reacts with carbon dioxide, then ferric carbonate is formed. Experimentally, it has been found that its free energy value is positive. On the other hand, for the backward reaction, the free energy value has been found to be negative. So why is it so? So it can be explained on the basis of the Lux-Flood concept. Actually, the AB value for ferric oxide is minus 1.7, while the same for carbon dioxide is minus 5.5. So the delta H value is minus 52 kilojoule per mole, and which is not sufficient enough to overcome the value of T delta S. So this minus 52 kilojoule per mole value is less than the T delta S value. So as a result, delta G has been reported to be positive. That means the delta G value, that means the free energy value for the backward reaction, that means the decomposition reaction, is negative. So this is thermodynamically feasible. So the backward reaction takes place, that means the decomposition reaction takes place. So this is the explanation on the basis of Lux-Flood concept that the ferric carbonate is an unstable compound. Now have a look in the acidity parameters A for acidic, basic and amphoteric oxides. So water has been arbitrarily taken as 0, and now preliminarily the alkali metals. So the oxides of the alkali metals, lithium dioxide, sodium oxide, this is actually I think Li2O. This has been misspelled here. This should be Li2O. Okay, sodium oxide, K2O, Rb2O, cesium oxide. Okay, look, the more the basic is the oxide, more negative is the value. Now from lithium oxide to beryllium oxide, it has been found that the negativity decreases. That means according to the period from left to right, the acidity parameter A becomes more positive. Now here you find that the highest value is for cesium oxide, that means the lowest value is cesium oxides, it is minus 15.2 kilojoule per mole. On the other hand, the highest value has been found to be here for Cl2O7. This is plus 11.5. So this is we can conclude that more positive the acidity parameter, more acidic is the substance. On the other hand, more negative is the acidity parameter, more basic is the substance. So from alkali metal to alkaline earth metal, the basicity decreases. See here, Li2O is minus 9.2, on the other hand BeO is minus 2.2. Here Na2O is minus 12.5, on the other hand MgO is minus 4.5. So along the period the acidity increases, while along a group the basicity increases from on descending. So the periodic property has been validated according to the Lux-Flood concept here, that from left to right the acidity increases, and on descending a group the acidity decreases and basicity increases. So these are the utilities of the Lux-Flood concept, which is particularly limited to the molten oxides, and the drawbacks of the Protonic concepts could to some extent be obviated by this theory. So that's all for today. Thank you.